Let's talk about section 5.2, which is all about logarithmic functions. We're going to learn how to graph and evaluate those functions. We're also going to learn how to convert them between the two, as well as we look our way through these, learn about common log and natural log and applying some of the properties with it. Now, for basically our problems that we need to know what a logarithmic function is. And a log basically is defined as y equals log base b of x. Where again, we have some rules. X has to be greater than 0, b has to be greater than 0. Now we will say b cannot be equal to 1, and that is basically a log-based function, so a logarithmic function with base b. Now, if you look at that really closely, that log base b of x equals y is actually also defined as x equals b to the power of y. Now, when you see this written out, a lot of times people don't see it written in this formula the way they see it here, as they see it basically as if I have, and you can choose any letters as you work your way through these. So be aware that the letters could possibly change. But what we're going to do is we're just going to kind of really focus on the fact that we have y, oops, there we go. Let me put that pen back on. Y equals b to the power of x, and then you'll see this kind of double arrow, and then they'll say, well, log base b of y equals x. Now it kind of goes in what we call a roundabout way. So we always start with our base, and our base becomes now the base of the log. And what was the exponent has now what it's actually equal to. Now these are actually inverses of each other. So the inverse of an exponential is a log, and the inverse of a log is an exponential. They go actually hand in hand. Let's practice this out a little bit, and let's actually work with some numbers, okay? So with our first one here, we'll start here. Always start on the base, okay? So no matter what you do, you always want to go where the base is, okay? And with my base, we're always going to say, okay, well, I have log base 4. Now, one of the things that I would suggest doing is make sure that you write this 4 as if it was a subscript, okay? And I always like to start with the log base because that's kind of where we want to start when we look at this here of 4 squared equals 16. Now we know that 4 squared equals 16, but we also are now going to learn that log base 4 of 16 equals that exponent of 2, okay? And again, kind of to help you out there, we kind of start at the base, and then this goes inside, and this is now what it equals. It kind of makes this whole circle thing, okay? Let's try that again. So again, start with your log and then go over here and find what your base is. So it looks like 7 is the base of that exponent there. And then I'm going to put opposite side of the equal sign is what's going to go in. So I have log base 7 of 1/7 equals -1. Okay. Now, even though this one is 8 to the first power is 8, and again, I know 8 to the first power, we normally let that 1 go invisible, but for right now, we're just looking at converting here. So I'm going to write log base 8 of, again, always start with where is the base, then cross over, and that's what goes inside, and then equals, and then cross back to the exponent. A log always equals that exponent. Okay. Now, a lot of these, it's really nice to see. You'll notice almost the first 3 here, all of my bases were on the same side. That's not always the case on D. So again, it doesn't matter where my actual base is. We always need to find the base. And again, our case here, it's base 5. Okay. And it's log base 5 of, cross the equal sign, so x equals y. Now, some of these you'll be able to plug in your calculator and some of these you won't. And right now, all we were looking at was converting them. So going between them and able to get the different formations that we have there. Now, again, this is still just using that whole, if I have basically some base to a power equals y, and we can convert it to basically log base b of y equals x. Okay, and that's all we did. This was the formula type thing that we used, and this is something very important that you want to remember. The double arrow is basically meaning I can go from one to the other. Now, if I have in this exponential form, we can go into what we call logarithmic form. So let's try that again. I want you guys to try it now. So go ahead and pause the video, work these out, and again, work to see, can you get going from exponential form to logarithmic form? Again, remind yourself what we refer to as exponential form is basically when we talk about y equals some base to the power of x, that is our exponential form. Now our logarithmic form should always have the word log in it. Okay. And when we work on these, one of the things I would suggest as you're working on them is when you type in log, make sure that it goes big and bold and black, and that will really help you out. So in our case here, again, we would have log base 10 of 600 equals x. And then this one here, we would have log base e of w equals 6. And then here we would have our log base g, I know, of 172 equals 4. Now, you'll notice that on the top two, I wrote parentheses around what I'm plugging on the inside, and then on my third one, I didn't. The parentheses are not 100% necessary, but I find them really helpful for myself just so I know what is actually inside the log versus what is actually the base. And if you have really, if you actually have like really, really strong, like big writing, so if you write really big, I do strongly encourage you to use the parentheses. When you look at it in the homework, they don't normally put the parentheses. So most books, when you read them, they don't have the parentheses there, but they've typed it out and they've got better handwriting when it's typed out. So keep that in mind. Now I am going to put a notation by two of these because two of these are actually kind of special. And that's this one and this one. These two are very unique because they are special ones for us. They happen to lead us into what we call a log, two very common logs that we use so often. Okay, so instead of actually writing log base 10, we would actually rewrite this as just log. And instead of writing log base e, we would rewrite that as ln. Okay, and again, we kind of learned a little bit about these previously, so just kind of keep those in mind that instead of writing log base 10, I would write log, and instead of writing log base e, I'd write ln. And again, this is ln, not in. It's natural log. Okay, so again, if you can go one way, you've got to be able to go the other way as well. I suggest every time that you work on these, that you go ahead and write down that format. Now, again, we normally write the format down going with our exponent first and then into our logarithmic form, but this doesn't actually matter. If you would like to write the exponential form second and the logarithmic first, then you can. Or you can just remember that this is a two-way street. Again, that's why the arrow's got double arrow on both sides. So we start with always at the base. So start by finding your base. And again, that's always going to be the key. So I'm going to have 2 to the power of 5 equals 32. Again, start at the base, cross the equal sign to get the other part, and then cross the equal sign again to get what it equals. So again, start at your base, cross the equal sign to get your exponent, equals, cross back, and what's inside, that is going to be what it actually equals. Okay, so in our case here, again, base is 8, exponent is what it equals, and then 1. So again, start here, go here, go here. Kind of creates a bit of a circle, okay? Now, again, as you guys are working these, one of the things I will kind of make note of is that when you do work these, this is not normally shown. I just put it there to kind of help you out. But again, this is again not normally shown. So normally you would just see log of this number here, and you'd have to remember that it's base 10. So I want you guys to try this. So again, pause the video if you need to, give it a second, try it out, and again, go from logarithmic form to exponential form. Okay, so hopefully you've had a second to pause and worked it out. Again, this one here, you'll notice as I go log 15 equals y, there's no base written, but it is understood. So as we do this one here, again, this is an understood base 10. So 10 to the power of y equals 15. And again, same thing with this one here. It's a natural log, but again, it's not written as what that base is. It's an understood base e. So again, that's where we start with our base e to the power of w equals k. And then nicely on our last one there, it actually had the base written. So 4 to the power of m equals p. Now that we've converted going from one to the other, and again, be very careful. Sometimes when we talk about these, when we say write the following as a logarithmic or exponential, or if I say the word convert, please understand that there is no solving involved on this. We are not solving for anything. We are just converting. So let's talk about graphing. So let's graph y equals a log base 5 of x. Now, as we graph these, it might be helpful just because we've never really dealt with logs before to really kind of maybe convert it. So let me start by going, oh, right, well, this is basically the same thing as 5 to some power equals x. Okay, and that might help out a little bit there. Okay, so when we do it that way, 5 to what power would give me 1 over 25? Well, in our case there, that would be -2. Give me a second. That negative sign went a little on the randomness. Okay. 5 to what power gives me 1/5? Well, 5 to the first gives me 5. So if I need it in the bottom of the fraction, we're just going to put a negative on there. Okay. 5 to the first power is 5. Sorry, I wrote that in the wrong thing. So 5 to the first power is 5. So that's going to be first, that number 1 there. And then 5 squared is 25. So that tells me 2 has got to go there. Now, what always gives me back 1 is when I have an exponent of 0. Okay. So now that you've got all those in there, you kind of want to plot them and graph them. Again, these are my x values, and then these are going to be those y values. Okay. Now, for those of y'all that have a calculator, you're definitely probably going to want the calculator to help you out a little bit. And again, you can use a calculator, or you can even, you know, if you need to pull up like maybe Desmos or something, some type of virtual graphing calculator, that works as well. Just remember on a test, we don't really have access to some of the things. So let's go here and we'll go to y equals, clear it out. Okay. And since we've got log base 5, so remember, we kind of did it by hand, kind of thinking our way through how we got all this. But in our calculator, we want to graph log base 5. And to do that, there is a way in your calculator. Okay. Now, this is going to depend on whether you have a TI-83 or an 84. So guys, keep that in mind. Okay. My graphing calculator is a TI-84. So I'm going to show you kind of the trick for you guys first. And then I'll go help my TI-83s a little bit there. Okay. So alpha, and I believe it's zoom. Nope, sorry, window. I was right in the first place. So for those of y'all that have the TI-84 Plus and you have this ability to do the pop-up menu, it's going to be really great. Number 5 here is your log base. And again, it already has it there where you can plug in your 5 and then plug in your X. Oh, got to be in Y equals before I do that. Sorry. Okay. So there's my 5 and there's my X. And then just zoom 6 to graph it, make sure. Now, as you see here, this is kind of what it looks like in the graphing calculator. And this is what I actually have here. This is kind of where the lies the calculator can tell you is this actually does keep going down and down and down forever. If we actually zoom in, so if I really adjust my window to really kind of take a peek in there, this will actually show up more and more if I look at this area in particular. It just gets so close that the graphing calculator cannot graph it and show how close it actually is. But if you were to really kind of look at it and zoom in around that area, zoom in, there we go. Let's see. As you can see, I'm tracing it and we're like really, really small. But the moment I get to my x's being negative, it didn't work. So, but as you can see here, like we're just moving so it's so small. So it's really hard in the calculator to really visually see this. And this is why sometimes it's harder to see these in the calculator, but it's possible. Okay. For my TI-83s, or those that don't have the pop-up menu, what you want to do is you want to be in Y equals and hit the math button. Okay. And then you're going to, on the math button, hit the up arrow, you can arrow down as well, but the up arrow, and look for log base. Okay. And then you can plug it in. For those that don't have the log base, we have to actually use a slightly different method. And we'll learn about that a little bit later in this section, but I don't want to overwhelm you too much just yet. And I don't want to show it a little early. So I'll give you guys a heads up in a second on that. But if you look at this, this is actually kind of the base shape of it. So if my log base, so if my base is like bigger than 1, this is kind of the shape of the graph. And if my base is between 0 and 1, meaning my bases could happen to be fractions, which is totally possible, but my base cannot be negative, okay? So the base is always positive. It's going to look like this. And again, this was something like when we talked about if my base on my exponent was bigger than 1, it was going to increase. And if my base was smaller than 1, but again, between 0 and 1, it was going to look like it actually decreased a little bit there. Okay. I do suggest that as you're looking at these, find kind of the x-intercept on this. That is the point. Now, previously we talked about the y-intercept being the point that you really want to pay attention to. Now it's the x-intercept, and this is basically, again, their reverse order. So let's explain how each one of the graphs can be found by comparing the two. Now you'll notice I'm using log, which makes it a little bit easier for those of y'all that have the TI-83s to be able to work on these. Now remember, with a log itself, that's just this right here, that button that says log right there. Okay, and we're going to start with just the base. So again, remember I said take away anything that's being added, subtracted, multiplied, or divided. Okay, anything that's a base or an exponent is still fair game. So I need to make it a +3. Okay, and let's compare those two graphs. So this is going to be my parent function, and this is going to be that +3. Again, where is that +3? It's on the inside, so it should be some type of horizontal movement. And I notice there I am kind of moving horizontally to the left. We can see that it is actually moving to the left, and it moves left by 3. Okay, so 1, 2, 3. I know like this puts on -2 here, but again, I'm moving 3 places. And again, if I move 3 places, 0, -1, -2. Okay, let's go with the next one. And again, let's kind of keep that idea down and really kind of work our way through it. There is, as we look at them, take a peek and start with what exactly is not that base shape. So what I suggest is kind of look for this, anything that's being added, subtracted, and remind yourselves of those transformations that we learned in chapter 4. Okay, so again, anything that's being added, subtracted, multiplied, or divided. So I'm going to highlight, let's see, I've got this thing here and this thing here. Again, here is my lovely base function. Okay, so we see here's my base function, and notice my base function looks like it's kind of moving up. But again, not only does it look like it's moving up, it looks like it's kind of moving over. But this time it's moving to the right. Okay, so I'm moving right. Okay, so moving to the right 2. And then I'm also moving up 4. And again, up 4, right 2. Again, notice where that -2 is. It's on the inside. Where's that +4? It's on the outside. Vertical stuff on the outside. Horizontal stuff on the inside. Now you'll notice there's a vertical asymptote at x = 2, and that's basically because we start with a vertical asymptote always, and our vertical asymptote here is x = 0. And so anything where x = 0 and smaller will not exist. So even though I've shifted the graph, that vertical asymptote also shifts. Let's look at this one here. So 1/3 log x. And again, let's just kind of look for what is different. So I'm noticing that right here, the 1/3 is being multiplied. Again, here is my base function on the graph there. So again, we've got our base function. And notice what's happening. I'm multiplying. So anytime I'm multiplying, that's going to be a stretch or a shrink. In our case, it's on the outside. So since anything on the outside is vertical, so that means I took the graph kind of holding it here, and 1/3 looks like I kind of shrank it, kind of smushed it in this way. Again, so here's the original graph, so see how it's like smushed. So we can say that basically we actually compressed this, and we compressed it by a factor of 3. And again, I know I'm compressing it because that number was actually smaller than 1. Okay, so remind yourself that we did talk about this, but I do want to bring it back to your attention. And I did kind of just briefly go over it, but basically natural log is basically log base E, okay? And this is something that this is kind of its own formula, but it's one that we just kind of keep in mind. And when we look at natural log, it is actually in our calculator. So if you take a peek at your calculator here and take a peek right here, there's that ln. And again, it's ln, not in, guys, ln. Okay. And if you kind of want a little bit of extra hint, so a lot of people don't actually begin to notice this, but if you look right above the ln button in blue, again, the same color as your second button, that's where we got our beautiful E from. So again, E and ln go hand in hand. And again, this is called our natural log. This is actually something that shows up quite commonly, okay? And we do see it an awful lot. For those of y'all that move up into, like, say, calculus, natural log is going to be a really big thing. For those of y'all that move into, say, college algebra, you're definitely going to learn a little bit more about them. All right, so let's look at this word problem. So projections from 2010 to 2050 indicate that the percent of US adults with diabetes diagnosed and undiagnosed can be modeled by the following function. Again, if they show you a model, it's normally super important. So let's highlight that. They gave me a formula. Now in this formula, as I look at it here, it says that I have a negative 12.975 plus 11.851 natural log of x. Everybody see that? Natural log of x. Now x is, again, the number of years after 2000. Okay. That is also something else that we want to make a really good note of. So x is the number of years after 2000. So we're going to start by graphing it. Okay. And with our graph here, then we're going to talk about, is it increasing or decreasing? And then that's going to be really helpful if we just look at the graph for that. And what does it mean in the context of this problem? So what does it mean if we're increasing or decreasing with these types of words involved? Okay. What does this model predict the percent of US adults with diabetes in 2022 is going to be? And then we're going to use the graph actually to estimate what the model will be to predict the 33%. Okay. Okay, so let's just start with graphing it. And again, let's pull out that graphing calculator to kind of help us out here. And with that graphing calculator, we are going to hit the graph button there. Again, I have stuff in there, so I'm going to go ahead and clear it out. And again, this is just this right here. So I have our negative 12.975 plus our 11.851 times our natural log of x. Okay, again, that's just me putting it in there. So again, not a big deal. Okay, so we've got it in there. And again, I'm just going to zoom 6. So I always want to kind of start with this really fresh graph when we do that. Now from there, we can make adjustments to the window if need be. And in our case here, I'm going to kind of bring back to your attention that this was only valid between 2010 and 2050. And we know that x is the number of years after 2000. So again, x equals 0 is the year 2000, which means basically I'm not really looking at any negative style numbers there for my x value. So I'm going to go into my window and just go 0. Okay. I am going to kind of, again, remember we're going up to 2050. So like, let me go back to that window and go, okay, well, if this is my 0 year, that means this is about 60 years later. So let's just go all the way out to 60 there. Again, once I do that, I can't really see how far up this goes. So let's go ahead and go to my Y max, and maybe this is a percentage. So like, let's just go up to 100. And again, Y min, we're not really looking at it. So it's just going to be like, just let it be 0, or I'm going to say -1 just so I can see this down here clearly. Okay. So we can see it's never going to be 100%. We really don't want everybody to have diabetes, right? So maybe 100% is too high. Let's just do 50, half of it. All right, that looks pretty good. So again, here is that nice, lovely 2010. So that should be all the way to 2050 is where this kind of models goes from. Okay, again, but I am starting at 0 and this goes all the way to 60. So, okay, so we've graphed it. Now, as we look at that graph itself, take a pretty peek at it and go, okay, let me flip to the next slide there. What does that actually mean? Are we increasing and decreasing? Well, in our case here, the first thing I begin to notice is that we do look like we are, if I put my little person up here and kind of walk my person up, it looks like I am increasing. So I'm going uphill. So we know we're increasing. Okay, so the function's increasing, which means, again, we're increasing what? What's going up? Well, these, remember, were the percents of people with diabetes. So as here, these are the years. So as I go this way, my years increase, the percent of diabetes also increases. And that literally just answers your question right there. So basically, you know, the function's increasing, which basically means the percent of US adults with diabetes is predicted to increase between our years. Okay, so let's say, what does the model predict in the year 2022? Okay, so in our case here, again, with this one here, what we're going to do is we're literally this versus this slightly different problems. What does the model predict? Meaning I need to plug something into the model. So we're going to take 2022 and switch it into how many years after our 0 year. Now remember, our 0 year here was 2000. So that would be 22 years later. And all you have to do is plug in 22 into the function. Okay. Now, once you've plugged 22 in the function, you're going to plug it in and evaluate. Now, you will get a decimal answer just because the natural log of 22 is not a pretty number. And in our case here, just go ahead and round it. It's going to tell you in every problem what to round to. Now, again, what does the model predict? Meaning you're plugging into the model. In this one here, use the graph to estimate the year. Okay, slightly different here. Estimate the year in which the model predicts the percent will be. What does the model predict the percent? In what year does the model predict this percent to reach 33%? Now, again, currently we don't have enough way to do this by hand just yet. We'll learn. We're going to get there. But for this one here, we're going to use the graphing calculator. So we're going to plug in our function, and then we're going to plug in 33 and find out where they intersect using that intersection method. Okay, so with our case there, as we take a peek at it, again, just really kind of look at that there, go into y equals, plug in 33 here, and then graph, and then find where they intersect by second trace number 5. Okay, first curve, see how it says first curve, hit enter. Second curve, hit enter. And then your guess is the third question there. Again, move it as close as you can to the guess. It helps tremendously to be close to it, and hit enter, and it should give you. Now, if your last couple of numbers are slightly different from mine, it could be because one, you haven't adjusted your window to the exact same windows as mine. So if your windows are slightly different from what the problem is kind of helping you to tell you what the windows are, that could be why the last few digits, but the first 2 or 3 will always be right on. Okay. Now, when we look at that there, we end up with 48.3, which basically, you know, even if you round up to 48.4 there, that means that basically it's 48 and into the next year. So that would be 49 years later. So in the year 2049. Okay. So let's go ahead and add some of our basic properties in there. Now I am going to kind of put this up there. These are going to be things that you want to write down. And again, remember when I said that this chapter here, there's going to be a lot of formulas. These are going to be some of those formulas you really want to write down. Okay. So this is just our basic formula, log base b of b equals 1, meaning basically if I have, say, log base 5 of 5, we know that that simplifies out to be 1. If I have, say, log base 4 of 1 here, well, we know that's automatically going to be 0. Or if I have, say, if I can see log base, we'll say 6, and then we have 6 to the power of, say, I don't know, x, then because this base and this base, there's 2 bases up here, the answer just simplifies out to be x. And it also goes the other way. So if I have 6 to the power of log base 6 of x, Again, I've got a base of an exponent and the base of a log. They're identical. As long as they're identical, then that answers what's inside this log. Okay. So again, write these down somewhere. It's really, really helpful. Again, do you have to have these memorized? For this class, no, but I would strongly encourage it for those that need to move up into college algebra and calculus, especially in calculus. Calculus, these come back with a vengeance. Now, is everybody in this course going to calculus? No. So just keep that in mind that it's something that could happen if you move up in your higher level math classes, that a lot of this stuff does make an appearance again. For those of y'all that are not going up any higher, but you're still going to take some type of math stuff, these come in a little handy for my business people. Okay. Now down here, really, really simple one is just basically if I have a log of both sides, and again, as long as these actually share the exact same base, then we can basically say the inside's equal. Now on number 5 here, we normally do write it a slightly different way. And I'm going to write it in the other way that most people normally write this down to kind of keep it memorized instead of writing it down as this big formula. Okay. So what a lot of people end up writing is actually that if I have log base b of m equals log base b of n, then that's the same thing as saying that the insides of those logs are equal. Okay. And again, this is kind of something that a lot of people write instead of writing it out in the format that you can see here. Now, I'm not done, so be aware, we are totally not done. So let's add in a couple more. And again, these are the ones that I would strongly encourage with even more. These are the 3 that are referred to quite a bit. Okay, these actually have given names. So when we refer to the product rule of logs, number 6 is what we call the product rule of logs. This one is referred to the quotient rule of logs. And this one is referred to the power rule of logs. Okay. Again, super, super helpful to keep these in mind. I do remind you that, again, product means to multiply. So if the insides of the logs are multiplied, then everything inside that log that was multiplied against each other can get its own log. Again, must keep the same base. Our quotient rule, quotient means to divide. So if there's 2 things being divided in a log, they can each get their own log. Again, the difference between the product and the quotient is the product rule is going to put a plus sign between them and the quotient rule is going to put a minus sign. Be aware that when you do look at this one, especially this one here, whatever's in the bottom of the log will always have the minus sign in front of it. Okay, and the last one is a power rule. And basically, if I have a power up here, that what we can do is we can take that power and pull it down to the front and multiply it to the log. And that's the power rule of logs. Again, 3 stars, very important to know that these are going to come back and they're going to be needed to be used over and over and over. So we're going to start by just practicing doing a little bit of rewriting. So here are 2 problems here. So log base 5 of x plus 3 log base 5 of y. Again, what I want to do is I want to write my answer as a single logarithm, which means my final answer down here should just say log base 5 and just have one thing. So there should be nothing else. So to start off, the best thing to do is start by look in front of the logs. Okay, so look in front of them. Okay, this part right here doesn't count. There's a 1 here. So again, it's invisible. Just let it stay invisible. But here's a 3. So what I'm going to do is if there is a number in the front there, whatever it might be, take that number and pull it up. Okay, so really, really helpful to have that. Again, whatever that number is, take it and pull it up. So we're going to start by basically having our log base 5 of x plus log base 5 of y to the 3rd power. Okay. Now, if there's nothing left in front of the logs, now we look to what's between our logs. Now, between my logs here is addition, and we said that with addition, that meant that you take the insides of those logs and multiply them. And again, when we multiply, we normally just write them side by side. Okay, so let's try again. So again, look to the front of the logs. And again, if you see anything in front of the log, we are going to go ahead and pull them up. Now you'll notice when I say in front of the log and pull up, you notice I am not pulling the minus sign, I'm just taking the number. So leave the minus sign alone. So just take the numbers, pull them up, or if they're letters, pull them up again. And then from there, we look at what's between the logs. And in our case here, it is a minus sign. And a minus sign means I'm going to divide the insides of my log. Okay, now I'm on this one here. I'm not going to say that's my final answer just because we have to remember our exponent rule. And some of you guys may have not remembered it, but we did talk about it. And it's one of those things that you keep in mind your exponent rules. So log basically is going to be log of the square root of a divided by b to the fifth there. Okay. So let me go ahead and put that in a really nice written format. So let me erase all my ink and put it in the format that's a little bit nicer to see there. Okay. And like I said, just be aware that with this one here, that as we, as we take a peek at this one here, we normally do, it can be this, or it can be written as with the square root symbol. So just keep that in mind, that it could have the square root symbol there. Okay, let's try again. So again, start with look at what's in front of the logs first. Now in our case here, this isn't a log, it's a natural log, but same rules will still apply. Remember, natural log is nothing more than log base e. So as we start there, we're going to start by taking that 2 and pull it up. Okay, so it's pulled up. And now we look at what's in between. Okay, and it's a minus sign, so we divide. Let's go a little bit harder. Okay, so why don't you guys try this one now? And again, pause the video if you need to. Okay. Okay, so I'm going to walk us through it. So again, we'll start with, let's go with what's in front of our logs first. Now, in our case here, I am going to be a little cautious because notice this part right here, that is x plus 1. And that is more than just one item that we have like here. So what we want to do with this, because of it being multiple items inside the set of parentheses, instead of putting the power on the inside of the parentheses, we're just going to hang it up here on the top. Okay, so we're going to put that power of 2 there. And then once we've done that, we're just going to look at what's between them and then divide, because the minus sign means to divide. And again, this is just x plus 1 quantity squared. Just leave it just like that. Don't even bother to multiply it out. And we've just now used the power rule and the quotient rule. Okay. That is our nice, lovely chapter. So again, if you have questions, go ahead and ask. Be sure to really write down all these rules and really practice them. It's going to really help tremendously to practice an awful lot on these.